Hi, this is Geoff Goldman with the U.S. Army Research Laboratory. The title of my talk is Propagation of Audio Signals from Elevated Harmonic Sources. For those of you who know me but don't recognize me, this is my new COVID-19 look, which I may or may not keep in the future. An outline for my talk is first I'm going to talk about 4 models that are standard and then 1 new model. Then I'm going to talk about interpolating the results from the model and doing some simple signal processing and end with conclusions. The motivation for my talk is that it's usually difficult to get a good elevation estimate from traditional beamforming algorithms. And if you start to include some of the physics into the propagation, you can do a better job testing as well as developing better beamforming algorithms. I'm modeling the propagation using a stratified atmosphere with a moving media. Pierce describes equations used to model this, which I'm using. You need to have wind profiles, you need to have propagation speed profiles and initial distance, and what you get out is that you'll get an array of the path of the signal. To generate the propagation speed and wind speed profiles, I'm using another model. I'm using this Monin-Oberknopf similarity theory. You input the environmental parameters, some initial wind speed, initial temperature parameters, and you're able to generate profiles. I'm using the code that was given to me by Vladimir Ostashev, which I'm very grateful for. So this is a standard approach that seems appropriate, and it's also used in other applications. I compared the results of the code I wrote to another algorithm that I downloaded from MathWorks website. It was written by Schmidt. The results seem very similar. There are small deviations at the top of my trajectory, but the code seems to be reasonable. I also, this only tests the propagation speed. I also did some simple tests with wind speed, and that also seemed to give reasonable results. I'm using a standard model for the ground reflection. I want a simple model, so I'm using the Delaney-Baisley, which is a 1-parameter model, and another model developed by Keith Attenborough, which is a 2-parameter model. You get a reflection coefficient out. I'm using some code that was given to me by Kirk Albert, so I appreciate that. This is all very standard models. Now, I'm also modeling the indirect path, and I'm assuming I have a flat Earth. And since I have a flat Earth, I can propagate this indirect path shown in the blue, which would bounce up and hit the microphone, as ending below the Earth. And so now I have this virtual microphone location, which is equivalent, but it will be easier to process. It will be easier for me to write software and process. So I don't need to generate one ray, I need to generate a bundle of rays. I need to calculate what angles to generate them from. And the way I do that is I start out by inputting this red box shown on the right, and then I need to adjust a grid of theta and phi angles so that the rays accompany the box and also, my microphone array. So this slide shows an outline of the algorithm I'm using. This is somewhat of an ad hoc algorithm. I start out by doing a Taylor series approximation. So this term over here kind of looks like a Jacobian. Then I do a least squares fit, and then I either do gradient descent, or if I get stuck, I just randomly look around. And this seems to give reasonable results. So now I need to find the time delay associated with an array arriving at each microphone. My original plan was to just use MATLAB functions, but there are no MATLAB functions available for this because the grid is irregular. So I wrote my own algorithm. It's a 3D interpolation problem, but I broke it down into a 1D, then a 2D. So first I interpolate along the z-axis, then I do a 2D irregular interpolation over the x and y axis. And all this is just linear, and I seem to be getting reasonable results. So I've looked at extending this to doing a little bit of better job. So there are a lot of techniques for doing interpolation. Seems to be the more complicated the processing, the better the interpolation. It's not clear what the best approach to go with. So this is an area of further research. This shows some of the results for the propagation time errors from the linear interpolation algorithm that I wrote. On the bottom, you can see the rays that are being generated by the blue dots, the location of the microphones by the red X's. I have 7 microphones. You can't see the ones in the z-axis because they're going to be stacked on each other. The errors are seen on the y-axis in the top figure. They're pretty small. Once you get reasonable number of rays, the errors seem to be under a microsecond, which is small. So, these rays all have a positive bias, which is a little bit disturbing. So then I started to look at the reason for the positive bias. If you look at the differential time delays, they don't vary linearly. They have a quadratic component to it, and I'm doing linear interpolation. So it's not surprising that I have biased errors, but they are small and manageable. I also ran a simulation where I was moving my target. I didn't add Doppler, so it was like stopping, then moving, stopping and moving. And again, I'm getting small errors over this tetrahedral microphone array, all well under a microsecond, closer to 1.7 times 10 to the minus 7 seconds, which is quite small. Now that I have my time delays, I'd like to start to take into account other factors, such as turbulence. So as the microphones get further apart and the frequency gets higher, the signals can become uncorrelated. And the amount of uncorrelation can be modeled using this top equation. And this model was developed by Richard Kozak, Brian Sadler, Keith Wilson, and Sandra Collier. So basically, the turbulence increases as a function of frequency, distance between the microphone, and it's also affected by weather. And it is modeled by a complex Gaussian distribution. Now, I have an added complication of I need to find the distance between the turbulence associated with my virtual microphones. So, and the way I do this is I have a tangent line that's tangent to the propagation of the ray at the center, and then I find this purple line. I measure the distance between the real microphone and the ground bounce location. So that would be one element in my covariance matrix. And as opposed to if I was going to the third microphone, I would just draw a line up to my third and come down. So that's how I calculated distances. There's an additional complication. The ground can also cause some loss of coherency. And the way I modeled it, well, I want a simple model. And I did not find a simple model that I could implement. I didn't spend a lot of time looking for this, but I wanted to I came up with a very simple approach that right now I'm implementing. For the real microphones, there's no change. For the interaction between the real microphones and the virtual microphones, I just have a constant factor that reduces the coherence. The model where there's some calculations involved is with the ground bounce and the ground bounce. And here, I said the coherence is affected by the distance between the ground bounces times some constant, all to this e to the minus of this multiplication factor. So if they're right next to each other, there's no loss. If they're very far away, they're incoherent. This is a reasonable model. I'm still looking at, are there better approaches to doing this? So this model, I calculate this whole matrix gets multiplied by the old covariance matrix here to get a new covariance matrix, and it's just element by element. So even with this new matrix, which eliminates some of the singularities in the covariance matrix. If your signal happens to cancel due to the ground bounce, and your coherence and your signal is very coherent, then your covariance will also vanish. Now that's not happening, but I still can have singularities in the covariance matrix. And one way of handling this is to do this technique developed by Robotnato. I'm implementing this stuff just using MATLAB's Choi covariance function call, which is based on Chomsky factorization, and it has elements of this Robotnato technique, but it's more complicated. So now that I have my covariance matrix for the real and virtual microphones, I can just do a linear transformation with the ground bounce, with the reflection coefficient, and I get my new means and my new covariance matrices, and everything is nice and simple and well described. Okay, now I can generate simulated signals. So this shows simulated signals for a tetrahedral array. It's a narrowband model, so they're all going to be sinusoids. I can generate beamforming algorithms. So this is a beamforming algorithm that's just based upon match filter. I just take all the time delays and multiply. So I make up my steering vector from the time delays for each angle, and I just multiply them by the received signal. This doesn't have any effective turbulence, but this algorithm by itself should be an improvement over traditional beamforming algorithms. And it's a reasonable approach. And that's where I'm at. So in conclusion, I developed some software for simulating the signals from microphone, for signals arriving at a microphone from an elevated source, and I illustrated the performance of a beamformer using match filter approach. I have a fair amount of future work I'd like to do with this. I'd like to incorporate the covariance information into a new beamformer. I'd like to investigate the effects of model mismatch on the beamforming. I'd like to update the interpolation algorithms, and I'd like to extend the turbulence model from narrowband to a harmonic or wideband model. Thank you for your attention. That's the end of my talk.